all if you are in good health with this sudden winter, chilled winter. Okay. Now, if I remember, in the last class we have just discussed till the formation of the till the extended Langmuir isotherm. Am I right? Can anybody rectify me if I am wrong? I think we have just discussed up to the extended Langmuir isotherm and explaining the equation and explaining the graph, figure 4.2. Is it okay?
Yeah, yes, sir.
Okay, okay. So you have seen in the earlier discussion that depending on the adsorbed gas, depending on the composition of the adsorbed gas in a particular mixture, okay, whether it is 20-80 or whether it is 40-60 or 60-40 or 80-20, this adsorption content, total adsorption content or the total adsorption capacity, and in that total adsorption capacity, the individual gas adsorption capacity is quite different for the different gas for different composition. Obviously, for the pure gases, there is no such trouble for calculation, and for pure gases, the Langmuir equation will be the earlier one, the first equation, which is given discussed in the earlier in the discussion, equation 4.1. This is the fundamental equation. Okay, this is the fundamental equation for Langmuir for pure gases, where you have represented with DAF basis, that means dry and ash free. That's why the moisture and the ash content are coming out. Okay, you have to subtract this component, and the VL and B or PL are the Langmuir constants defined as per the norms. Okay, but if there is a mixture, then this equation is invalid because this is only valid for pure component gases. And when there is a mixture of the gases, some 2 or 3 different mixture, you have to go for the extended Langmuir equation, which is given by equation 4.5. This is the equation. Okay. Now, if we are going to measure this option isotherm, we have to run the isotherm test. Okay. Now, this isotherm test is a detailed procedure. The detailed procedure I'll be again discussing when after all this theoretical discussion will be moving into the articles or into the experimental part. But for the time being, to give you some idea, I'll be just discussing in brief. Okay, but I'll be coming back for the detailed experimental method later. Now, there are some steps you have to follow when you are going to establish this absorption isotherm. Okay. Now, if you read for doing any test, you have done the testing about the rock mechanics or any other testing, so you know that there should be some standard to be followed. There should be some purpose of the experiment. There should be some sample collection. There are some standards. There are some input and the output parameter you are going to take care of. Okay. So if we are going to divide the step-by-step process for establishing this option isotherm or the Langmuir isotherm as by the name of the Langmuir. So there are some steps. What are the steps? First is we have to select the sample and you have to prepare the particular type of the sample. Okay. Then the standards, according to the standards, which standard we are going to follow, we have to check. Okay, whether we are going to follow the ASTM standard, American Society for Testing Minerals, okay, after USA, the ASTM standards, or we are going to follow the Bureau of Indian Standards, okay, BIS, which is called the Bureau of Indian Standards, or there are some international standards are also given. Okay, and then we are going to perform the test, and then when we are going to perform the test, there are some different there are some setup of the experimental setup. There are some experimental conditions which is very much particular to some particular test, and then we are going to maintain the pressure, and we are going to calculate, we are going to estimate this gas adsorb, and we are going to equilibrate this. Okay, we are going to step by step process this. So if we are going to follow this note, it will be easy for you that if I go follow this note in brief. So the first is the selecting samples. Okay. Now the selecting samples, suppose when you are going for some testing, you have seen earlier that depending on the coal rank, depending on the coal composition, and depending on the coal grade. These three are very particular. These three are very much putting very much dominating on this gas absorption capacity. Okay, so obviously whenever choosing a coal sample, if you have some idea that this particular seam is having some higher rank or higher matured coal, or if this particular seam is having some very high ash content, then obviously you already know that you will not be able to get very high gas content or very high gas absorption capacity. Okay, but the actual capacity at actual temperature condition will be established by the isotherm testing. Okay, but for that you have to take the sample and you have to run the test. So first is that you have to collect the sample. Now for our experimental purpose, what we are going to do, collecting the samples, we can collect the sample by two different ways. We can collect the sample as some chunks, as some coal blocks. Maybe you can imagine that we are going to collect the sample as 1 feet cube sample. Okay, 1 feet cube sample, or maybe it is 6 inch cube sample we are going to collect, and then we can either prepare by a core sampling. Okay, by prepare a cylindrical core sample with a L by D ratio. Okay, as we are going to study for the UCS or the rock testing, or we can take some lump size. Lump size means some each individual pieces of the coal from that coal block will be average of 50 gram of the weight. By weight, it should be of average 50-gram weight. The way you have measured the product of strength index, do you remember the product of strength index testing? You have done it in the laboratory, rock mechanics lab.
Yes, sir.
Okay,
Yes, sir.
so when you are going to do that type of testing, you know that you have to break the rock, okay, and you have to prepare a 500 gram total 10 pieces, each having an average size of the 50 gram. So here also you can take each of the coal sample of 50 gram, and you can take the sample and you have to crush it. You have to crush it means you have to crush it to form a powder sample. Whenever we are going to take the isotherm testing, we are going to do it by a cylindrical core sample with L by D ratio, proper L by D ratio, or we can do it by powder sample. Powder sample means you have to crush it down with some fixed size range. How to establish the size range? The size range will be established by the mesh size. I hope all of you understand what is a mesh size. If not, then let me give you some idea that the US mesh size, there are some US mesh size also available. So let me show the screen also. Uh, if I yes, share the screen. Yes. Okay. I hope you all can see this sheet size window. Okay, so it is just a standard. This is just standard Wikipedia from the Wikipedia. If you just search by giving the US mesh size in Google, you will be getting a structure. You will be getting a table like this. Okay, you will see that there will be some sheet size given in millimeter. Okay, and the openings are also given in inch and the micrometer. Okay, and then there are the standard mesh size, which is the US mesh size. We are going to follow the US mesh size. You will see that there will be some numbers are given. Okay, now what this number signifies, the mesh size, if you see the definition, the mesh size, as you may have the idea from your mineral beneficiation lab, that the mesh size are the size which is defined by the number of the holes per inch. Okay, mesh size is defined by the number of holes per inch. So if you see the numbers, you may assume that okay, per inch these are the number of the holes. Okay, and it may not be the actual one, but it is estimated and it is used all over the world. Okay, and this, according to this standard mesh size, the fragments the samples or the particles which are prepared, the sizes are given in millimeter, in micrometer, and in inch. Okay. And you can also see that if you are going to increase the mesh size, suppose UH mesh size 4, which is having the size of 4.75 millimeter particle size, it is having the opening. Then if you go to mesh size 30, you can see that the millimeter opening is increased to 0.60. Okay, sorry, it is decreased to 0.60. So that means if you increase the number of the mesh, okay, the particle size is going to reduce. And if you are going to pour it, you know the concept of the undersize and the oversize over a size fraction. So based on this you are going to prepare some particular size range of the your coal powder. Because when you are going to break the coal sample, there will be some different size analysis, there will be different sizes, maybe some of them will be inch size, some of them will be some millimeter size, some of them will be micrometer size. And if you are going to mix your study of the adsorption capacity, it is established, and you may have also have the idea that the lower the size of the particle, the higher is the gas absorption capacity. The lower is the size of the particle, the higher is the gas absorption capacity. Why? The reason is that if you are going to take a chunk sample, suppose you are going to take a 6-inch cube sample, what you are going to get? You are going to get a coal slab, a coal cube, which is having only 6 surfaces. Okay, but the outer surfaces are only visible. The 6 outer surfaces are only visible, but in the innermost point, suppose if you are imagining the CG, near the CG or the surrounding some of the points through surrounding the CG, there is no surface area is exposed. And adsorption is a process where it is layered onto the surface. So the way you are going to break, the way you are going to reduce the size of the coal or the particle, what you are going to do, if you are going to break it down the sizes, you are going to increase the more surface area. Suppose you are going to break the 6-inch cube sample into two pieces, what you are getting, you will be maybe getting a 6-inch by 6-inch by 3-inch two cube sample, two rectangular slab sample. Okay, so you are getting 6 plus 6. So now you are getting 12 surface areas or 12 surface plane. So what is going to indicate? Because as you are going to get the more contact area, the adsorption or desorption will be much more than the earlier case. So when you are going to reduce the sample or reduce the particle size, the diameter or the fraction or the size range, what you are getting? You are continuously increasing the surface area of the particle. And as you are going to increase the surface area, the contact area, not the surface area, the contact area with gas, the gas can have a direct contact with the particle, which is not possible for a chunk sample. That's why if you are going to reduce the particle size, the adsorption capacity is going to increase. So the size, the range of the size or it is given by the particle diameter. This is also very much important, and it is established. I'll show you later. Then in some of the recent work, if you are going to increase the size, the particle size, the adsorption is going to reduce. That's why the mesh size is very much important. Okay, and you need to, when you are going to prepare the sample, you have to again be very much cautious about which size range you are going to act. Suppose if you are going to take one coal sample, for particular coal sample you can segregate different size range from the same sample. And so for each of the sizes you can particularly measure the isotherm, the adsorption isotherm. Or if you are going to take about some different 3 coal samples, suppose, then for each of the coal samples you can get a particular size range, suppose 40 to 60 or suppose 100 to 150. Okay, as it is given here. Okay, from UH mesh size, see 100 to 150. See, 150, 100 mesh size, this is the 100 mesh size, okay? And 100 mesh size is sample size is 0.150 millimeter. Whereas if you are going to compare the 150 size range, it is going to come nearly 100. So 100 mesh size is having 0.150 millimeter, and 150 mesh size is having the particle size having 0.100 approximate. So for three core samples, if you are going to choose that this range you are going to conduct the isotherm test, so obviously you will be able to compare the adsorption isotherm based on the particular size range. If you are not going to choose the same size range, again you cannot compare them. Okay, so when you are going to do the testing, you have to be careful because you are going to select the sample whether you are going to select a core sample, cylindrical core sample, or the powder sample. Now again there are certain advantages and the disadvantages. Sometimes we are going to choose from where you are going to choose the samples. Sometimes we are going to choose the sample from the drill cuttings. Okay, now if you are going to the mines, you know that you can collect the samples from actually from the face or from the freshly exposed strata. Okay, after the blasting or after the loading has been done, and when the loading is done, you are going to collect the sample, or maybe in the surface also, in the face you can collect the sample. Okay, now why this you have to be careful, because the gas which is trapped within the coal, when you are going to take a solid coal pillar, obviously if you imagine the solid coal pillar, the surface area are only four. Why? Because the upper and the lower, upper there is a roof, and floor there is, and the bottom surface is the floor, so these two surfaces are blocked, but the other four surfaces are available because it is surrounded by the open gallery. So if you are going to take any coal sample from these open surfaces, you may not be able to get any gas when you are going to do the disruption kinetics testing for the dissolved gas content. Why? Because as depending on the fractures present, depending on the other blast induced fracture or the other machinery movement or some other load or failure, the fracture will remain open. There may be new induced fracture will start, and so whatever the gases are already trapped, they will be coming out, so you will not be able to get any gas. So that's why you have to be careful when you are going to take the sample from the inside of the blasting or from the inside of the coal. You have to, hello, am I audible?
Yes, sir.
Okay, okay. So you have to collect the sample from the in situ or from a place which is not being exposed too much. Suppose if you are going to do any laboratory testing and if you are going to collect the coal sample, you will not instruct anyone to take the coal sample which is lying on the face. You have to take the sample which is just coming after the blasting, because in that part, when you are going to collect the sample from the freshly exposed roof after blasting, you have to take the coal sample and you have to wrap it up with the bubble wrapper. Why? Otherwise, as it was under when the coal is in situ, it is pressurized, it is having no contact with the atmosphere. So whatever gases are there, whatever pore pressure inside that, whatever gas pressure is there inside that coal, it is also remaining intact. But when you are going to collect the sample, okay, you are going to collect the sample and you are going to collect the sample and take it out from the in situ, what you are doing, you are going to release it pressure. So gases, if you are not going to trap it, the moisture will try to evaporate, and then gases also coming to the atmosphere, it is going to escape. Why? You must have heard about the virgin rock temperature. All of you know about this virgin rock temperature? Anybody?
Yes, sir.
VRT. Okay. The virgin rock temperature is some higher temperature which is constant if you are going to inside the strata from the outer surface, outer gallery surface. Okay. So obviously when you are taking a sample from the inside, its temperature is going to down, and you know that the temperature is also going to govern the sorption capacity. When you are going to take out the sample, if you are not going to wrap it up the coal sample, its moisture will also going to exceed. So whatever result you are going to get for the moisture, it will be erroneous, and then that it will be also giving you wrong data for the gas suspension capacity. So you have to keep it in the mind that first is that what type of sample you want, whether it is a core sample, cylindrical core sample, or whether it is a powder drill cuttings, and from the drill cuttings you are going to make it a powder sample. Next, if you are going to make it a powder sample, what fraction, what mesh size, or what equivalent diameter or the particle diameter will be there. If you are going to do the core sample, then again the smaller core or the larger core. If the core is smaller, obviously it will take some less time. If it is a larger core sample, obviously it will take some higher time. Why? Because large volume of coal will require very high amount of time to get the saturated or to expose or to dissolve the gases, because the gas content of a large volume of coal is much higher than the gas content of a small volume of coal. Okay, so small size and the time will also be a factor. Next, the third point is whether you are going to do the testing with dry sample or wet sample. For both the cases, if you are going to prepare the sample for dry testing or prepare the sample for wet sample testing, there are standard guidelines available you have to follow. I'll be sharing you details when we are going to the discussion for the laboratory. Okay. So for the time being, you will remember this point, that for the sampling, you have to keep in the mind three different facts. Okay. Core sample versus powder sample, from where you will be collecting the sample, and what will be the particular diameter, what will be the size range, and then what type of sample, dry or wet sample, and follow the accordingly, maintain the standard and prepare the samples, because sometimes the preparation of the sample will take 2 or 3 days depending on the type of the sample and the volume of the sample. Okay. And so when the sample is being prepared, now you are ready to do the testing. Here they have given collection of the sample and the crushing of the samples. So I have mixed these two. Okay, I have made the discussion amalgamating these two parts. So you have collected the sample, you have wrapped it up, and you are taking out to the lab, and you are going to crush it. You are going to prepare your particular size range, and then you have to refrigerate. You have to refrigerate the powder sample in a sealed envelope. Okay, so that if it is dry sample, no further in moisture can be going into the sample. If it is a wet sample, no moisture should be escape to the atmosphere. So that's why you have to put it in the separate envelope, sealed envelope, and you have to refrigerate it, because if it is becoming very much hotter, then again the moisture will escape. Okay, so this is the concept. Please go through these steps. Okay, try to understand. I hope you will be able to understand this. Now, when you have prepared the sample, now you know that depending on the coal sample, suppose a coal seam is lying from 100 meter to 150 meter of depth, and this dipping sample, and this spreading over an area of 1 kilometer. Okay, so now if you are going to do 10 different boreholes and you are going to intercept that particular seam at different depth, and you are going to take the core logs, okay, and from the core logs, when you are going to do the routine analysis for the porosity, permeability, or strength analysis, or so many property and density analysis, there is a obvious chance that these properties or that these values will be different, even if you have taken the samples from a single coal seam. Why? Because this is naturally prepared. You cannot say that okay, this is going to be same because it is from the same coal seam. because it is natural qualification processes there, maybe the formation or maybe the deposition will change the composition or the rank or the ash content or the moisture percentage totally may be varied. So 10 from the 10 boreholes, even if from a single seam, you can test and you may find some different seams, different results. Okay, but then you have to analyze and you have to check that whether you are going to take the average reading or not. If you are going to take the accurate sample, accurate results, then obviously you have to for each gas content analysis or gas in place analysis, you have to actually take the same value of that particular borehole. You are not going to allow the average value. And then when you are going to take the samples, you have to first you have to take, that's why when suppose you are going to take 10 powder samples from the 10 boreholes at different depth, and then you will be doing this isotherm testing. Now, as for the isotherm testing, you have seen earlier that we are going to express the gas absorption capacity per unit weight. That means SCF per ton, okay, or CC per gram. CC means cubic centimeter per gram, okay, or meter cube per kg, or SCF per ton, standard cubic feet, which is the 15.5 degrees centigrade atmospheric pressure, cubic feet per ton of coal. That means this much of weight, so per unit of weight. So when you are going to get the per unit of weight, the gas absorption capacity are going to be expressed in SCA per ton or kg, meter cube per kg, or CC per gram. These are the standard process of nomenclature of expressing the gas storage capacity. Okay. Again, when you are going to do the testing, before you are going to conduct the ASTM testing, you have to follow the proximate analysis and the ultimate analysis. Okay. The, the standard procedure for the proximate analysis and the ultimate analysis are there as per the ASTM method or as per the Bureau of Indian Standard method. Now, depending on what procedure you are going to follow, you have to maintain the same standard. All of you have studied earlier about the proximate analysis and the ultimate analysis, so I am just skipping the detailed procedure, but it is important for CBM. So you must know, you read by yourself about these two methods, so that if in industry somebody is asking you that what is the effect of proximate analysis and how it is done, you will be able to answer. Okay. So proximate analysis is going to give you the ash, moisture, volatile matter, and the fixed carbon content. Okay. Whereas ultimate analysis is going to give you the carbon, hydrogen, oxygen, nitrogen, and sulfur content. Okay. Now, why this is important? You know earlier that there are different type of measurement procedure or expressing procedure. Suppose sometimes you are going to express as in as receipt process. Sometimes you are going to express as in DAB basis. Sometimes you are going to express as in mineral matter content free basis. Okay. So for each individual representation, you have to know the each individual composition. Okay. And you have also seen that in the Langmuir equation, they are going to subtract the A ash percentage and WC the water content. So it is very useful to know about the ash and the moisture content. And as it added advantage, if you know about the ash content, then obviously you have some idea about the cold rank also. That's why it is very much important. Okay. So please go through the process of the proximate analysis and the ultimate analysis. Okay. The process I am going to skip as you have studied it earlier, but this is included in your syllabus. Nobody should tell me later, sir, you have skipped, so we have not read it. No, you have read it again and again, so I am just skipping it. Okay. So after you know this proximate analysis and the ultimate analysis, now you are having the various composition of the coal. Okay. What composition? The ash content, moisture content, volatile matter, and the fixed carbon content. And next is the carbon, hydrogen, oxygen, nitrogen, sulfur content. After that, there is another technique, another method Another component which you have to measure is the petrographic analysis. The petrographic analysis, what is petrographic analysis? The petrographic analysis will give you the concept of the coal materials. What are the coal materials? The liptinite, inertinite, or the vitrinite. Okay, this content. I have mentioned these things earlier, na, that depending on the various bands, coal is also having some material component. Did I mention it earlier? Anyone? Did I mention it earlier about the coal materials when discussing the various components?
Yes, sir. Little bit, sir.
Okay, yes, yes, little bit, because I'll be discussing this. This will be very much easy to discuss when I am going to actually discuss the results and relating it to the coal materials. But for the time being, you know that there are three type of important materials: liptinite, inertinite, and the vitrinite. Okay, so these three are the defined terminologies, and depending on the various properties, they are going to show very high or very less or not at all any gas absorption capacity. Okay, I'll show you or I'll send you separate note for this. Okay, so there is another testing which is called the petrographic analysis. Now, the petrographic analysis is also in India. There are some separate Indian standards. Okay, it has to be done in the Simfar lab. It is to be done, and for this you have to prepare some 200 or 300 gram of the powder sample, and you have to prepare it at a particular size range, and you have to give it to them. Okay, what they will do, they will show you what are the different coal materials available and actually what is R naught percentage. Do you remember R naught percentage? I have told you earlier that R naught percentage is the vitrinite reflectance, which is measured, which is defined as the amount of light reflected from a polished coal surface under the microscope. So based on that, there is a classification which is classifying coal based on the VR naught percentage or the R naught percentage. So if you know the R naught percentage, accordingly you can directly put it the coal classifications, whether it is medium volatile bituminous or the anthracite or maybe lignite or pitch range. Okay, so this petrographic analysis will give you this idea about the directly about the coal rank, and this is very essential for the coal bed methane. Okay, next, you know they have shown it here the determining the moisture content. Now moisture is very very important. Why? Because of the fact that you know that the moisture is going to compete with the gas particle, and if there is any water saturation present inside the coal, so obviously it is going to block the free pore spaces which is otherwise accessible for the gas particles. So obviously it will be showing very less gas capacity, gas storage capacity. And then you have also seen that depending on the water saturation, there are different type of water saturation. There may be some mobile fluid saturation, there may be some immobile fluid saturation, there may be some equivalent moisture component, there may be some reservoir moisture component. Okay, do you all know about these terms? Mobile moisture content, immobile moisture content I have mentioned. Do you know the equivalent moisture component? Anyone?
No, sir.
Okay. According to the earlier discussion, there are some mobile and the immobile. Mobile means that some of the moisture will be taken out if you are going to heat it up. Heat the coal sample, some of the moisture will be transferred, it will be going to elapsed, and then this part, okay, whatever you have taken and some part it will be vanished to the atmosphere. So this part will be called the mobile fluid or mobile moisture content, which will be retained by the coal, that is called the immobile or the coherent or the sorry immobile or the connate water. Connate water, CONNATE, connate water you cannot take out totally, which is which is coherent or which is sorry which is inherent to the coal. You cannot separate that part of moisture, so it is called the immobile moisture, or that is going to refer as the immobile fluid saturation, because if it is mixing with the gas or oil and water, it is called the immobile fluid, otherwise it is called the immobile water saturation. After that, there is another term which is called the equivalent moisture. What is equivalent moisture? Suppose at some particular depth at a coal seam, there may be some of the water seepage and some of the moisture should be present. If you can get the idea, okay, suppose if you are going to add the water, so what will happen? The coal seam will be saturated with the moisture, and the way you are going to increase, the moisture concentration will be also going to increase, or the moisture saturation is also going to increase. At one point of time, you will see that even if you are going to further add water or there is a seepage of the water, the moisture level of that seam is not going to increase. That means the reservoir or the seam is totally saturated with the moisture at that pressure, temperature, and the depth condition. That means even if you are going to further add the water, the moisture percentage is not going to increase. This percentage or this moisture content is called the equivalent moisture content, which is called the saturated moisture content at that particular pressure temperature condition. I repeat once again, if you are going to get the saturated moisture content, that means the moisture which is already present in the coal seam, which should be present at some particular temperature pressure condition, then it will be called as the equivalent moisture condition, and the same will be referred as the totally saturated with the moisture. You cannot add any further moisture content. Okay. Whereas the as received moisture, you may remember, if you are going to take any coal sample from anywhere, okay, whatever the moisture it is having at that particular time, it will be called as a as received moisture, because after collection of this coal sample, soon you have to wrap it with the bubble wrapper, otherwise you are again going to lose this moisture. And remember, this is not the saturated moisture, or you cannot tell that whether it is saturated or unsaturated. Okay, so this is called the as received moisture. So there are particular technique for determining the moisture content also. Just even if your rock mechanics class, I think you have studied some of the porosity, density, and the water content measurement technique. Do you know this? Have you studied those things? The water content on the moisture technique. You have studied this in the laboratory, right?
Yes, sir.
Okay. So then you may know this. Otherwise, you read the process. Okay. You read it once. It will be easy for you to understand. The detailed testing method, again, I'll be discussing later. So that's why the moisture content is very, very important. That's why you have to be very sure about the moisture content. Okay. Next is the isotherm testing. Next is the isotherm testing. What is isotherm testing? Iso constant or the same, therm related to the temperature. So at a particular temperature, you are going to vary the pressure and you are going to get the volume of the gases that are going to absorb. Okay. What is the and you are going to follow here the material balance equation. What we are going to see here, the pressure, the temperature is constant. Okay, we are going to take some 6 or 7 steps of the pressure at uniform gap. That means suppose if you are going to measure the some testing from 0 to 7 megapascal, suppose at each 1 megapascal, so the pressure steps will be, first is the 1 megapascal, then 2 megapascal, then 3, and so on. So all are in uniform gap. Okay, and then at each of the reference, at each of the pressure injection, there will be some amount of the gases will be stored. Some amount of the gases, when you are going to send it into the cold, it will be, some amount of will be in the free state, some amount will be in the adsorbed state. Okay, and from the material balance equation, using the real gas law, PV is equal to nRTZ. P is the pressure, V is the volume of the gases. Okay, N, small n is the mole, number of moles. R, universal gas constant, capital R is the universal gas constant. constant. T is the absolute temperature in Kelvin, and Z is the gas compressibility factor. What is gas compressibility factor? With pressure, how much volume it is going to affect. Okay, how much compressibility it is going to affect, or bulk modulus related to bulk modulus. So with this, you are going to estimate the stage absorption. Stage absorption means at each point of steps you are going to get the absorption, and if you are going to calculate the total one, you are going to get the cumulative one. That means the first point will be the first after the end of the first. Okay, if you are going to take the gas step in this at the end of the second stage, you will be getting that stage and the cumulative absorption of the first plus second stage. At the end of the third stage, you are going to get the number of the gases absorbed from the second stage to the third stage, and again you will be going to get the cumulative one, which is the first plus second plus third stage of absorption. So this way you will be able to get the isotherm graph. Okay, but before this, let me give you some idea about this, how it is done. Otherwise, you will not be able to understand. So, if you see the schematic diagram, let me show you. There is a schematic diagram. Mm, I will be also giving you some of the other notes for this. Yeah, this is the schematic diagram. Okay. So this is your schematic diagram. Okay, please try to see what are the things are required. This total, this is a schematic diagram. Just to, there are two different cell. Okay, steel cells. The RC is the reference cell. Okay, and there is a SC. SC is the sample cell. Sample cell means these are the two steel or aluminum container. Okay, generally it is a solid steel component, SS314, high category of the solid steel container. Okay, with some fittings. I am not going to bother about the fittings. There are two containers. The reference cell is a void one, but the sample cell is filled with some amount of the cold sample, whether it is dry or wet. Okay, and then what we are going to do, the two the tool volumes are going to be connected with some valves and the switches, so that we can allow or we can take out the gases from there. Okay, the GS is the gas cylinder, PT are the pressure transducer to take the record of the pressure, and these two pressure transducer are going to be connected by the data acquisition system with the help of some software, and it is the results are going to come onto the desktop. So per second you can take what is the variation of the pressure, and this total thing, not the computer, not the data monitoring system, but the pressure transducer, the valve, the total setup. Okay, obviously you have to keep some pipeline which you are venting out to the atmosphere, otherwise there will be water will be coming into that. This total thing are immersed into the water or the oil fixed temperature oil bath. That means it is totally filled with either water or oil, and you have to constantly maintain the temperature at isotherm temperature, which may be 30 degree or 40 degree. Only 0.1, okay, 0.1 plus minus is allowed, variation is allowed. Okay, of the full scale. Full scale means from the total range of the measurement. Okay, so if I am going to measure, suppose I am going to measure that test at 30 degrees centigrade, so I am going to allow the temperature variation only 29.9 or 30.1, not more than that. If it is varying more than this, then there is a wrong. You cannot take the test. You cannot take the reading. And this temperature, this constant temperature has to be maintained by circulating of the water or the oil, so that each area of that water or oil container is having the same temperature. So you can visualize what is happening there. Okay, so this is the concept of the schematic diagram. I think I'm also having a figure. Let me just show you. I think I am having a figure also. Schematic diagram. No, sorry, it is not having there. Otherwise you will be able to understand. I'll show you later. I'll send you the defined note. Okay, so Once you are going to immerse it into the into the oil or temperature bath, you will be going to maintain it, and you will be going to hello,
Sir, you are not
hello.
audible, sir. Yes, sir.
Okay, okay. Yes. The connection was wrong. Connection was going out for some time. Okay, so if you are going to maintain it for 1 day or 2 days or maybe 3 days, it is required to get the immersion process constant, so that the oil and the water or the water bath and the total schematic, okay, the aluminum part or the reference cell, sample cell, and all the valves are having constant at the 30 degree centigrade. If not, if you are not going to allow some time, it may happen that the moment the oil and water bath is going to circulate, the total area is not going to be streamlined with 30 degrees centigrade. Okay, some part is going to show 30.1, some part is going to show 29.9, and this will put the error, because the Z factor, the compressibility, is very sensitive for the temperature and pressure. The gas compressibility for liquid and solid, it is much more less, but for gas, the compressibility is so high, it will increase exponentially. And I'll show you later that if you are going to get the variation, even if there is a variation in the Z factor, compressibility factor, in the sixth decimal point, after the decimal point, the sixth decimal point, okay, then also there's a change in the graph. Okay, then also there is a change in the graph. That means it is very sensitive to the temperature, gas compressibility factor. So what we are going to do with the gas cylinder, we are going to give some amount of the gas in the reference cell first. Okay, and at the first point, sample cell is no having not any gas. So the initial condition, reference cell is having some gas, and sample cell is having only the cold sample. So this is the initial condition. In the final condition, what we are going to do, we are going to open the valve between the reference cell and the sample cell, so that some amount of the gas from the reference cell is allowed to move to the sample cell. And then we are closing the valve. So reference cell will be having some initial and the final reading, and the sample cell also will be some initial. And then the moment you are going to put the valve close, as there is a coal and the gases are coming to the contact of the coal, it will show a decreasing pressure. Why? Because the gases are going to absorb in the coal. After some time, maybe 6 hours, maybe 12 hours, then it will be showing a flat line. In the testing, we are going to see if there is a no variation of the pressure in the sample cell within 2 hours or 3 hours, depending on the size of the sample, then we will assume that this particular stage has got the equivalent, or it has got the fixed gas storage capacity. The further absorption is not allowed, or at this pressure, the particular coal sample inside the sample cell is saturated with the gas. So no further gas can be added, and so we are proceeding to the next step. Okay, so in the next step, what we'll do, we'll add some other gas. So in the next step, the initial reservoir will be again increasing. Suppose earlier stage it was 1 megapascal. In this step, it will be 2 megapascal, and then it will be stabilizing. And then after stabilizing, we'll be putting some amount of this 2 megapascal gas into the sample cell. Now again the absorption will start. Why? Because the earlier stage at 1 megapascal, the equilibrium absorption has reached, but now the pressure has increased. So again the absorption will again increase. So you will again see there will be some absorption. And this way we are going to continue the absorption. And some 6 or 7 steps it will be required, so that we are going to get some graph. Okay. So this is the way. Again, I'm telling you that I'll be showing you the detailed step during the experimental part. You will I'll be also chapter 4 also they have also given some steps so that you can understand what are the steps to be followed to consider the absorption. Okay, to consider the acetone test. I think the time is over, so let me stop here. If you are having any doubt or any confusion, you can ask me. Any questions? Anyone?
Sir, can you send the material related to the setup so that we
Material
can
related to the
get?
setup. Acha.
Yes, sir.
Actually,
Test setup.
yes, I can understand. Actually, there is a appendix chapter where the detailed discussion of different tests are there. So I will be sending you this, but I don't want to stop the flow of this discussion. That's why I'm not sending it now, but I'll be sending it soon. So that because if I am going to send it now, na, we will begin because we are going to deal with the very much parameter, na. We are going to deal about the parameter for the storage and detailed parameter with the transport. If in the meantime we are going to start the discussion of the test, we may be feeling you it will be problematic for you to get the again the parameter from it. So that's why I am not sending. But as you have mentioned that okay, I'll be sending it. But be sure that for detailed steps and the discussion of the experimental part, I'll be discussing once I finish the chapter 4. Okay, I'm just giving you the idea so that you can correlate. Okay, any other question? If there is no question, then it is okay. And please be prepared for your class test also. Okay, thank you. Have a nice day.